Hey, what's up, guys? This is Chong. So let's take a look at 1707, maximum XOR with an element from array. So you're given like an array nums consisting of non-negative integers, right? And you're also given like a list of queries, which has like who has like two elements. The first one is x, the second one is the m. And the answer is the size of the queries, and each answer is the maximum bitwise XOR value between the x and any element of the nums that does not exceed mi. So in other words, right? So you can do any of the XOR. You can use any numbers who is smaller, not greater than mi, and do an XOR with the current xi here, and then you need to get the maximum of that. And if there's no such number exists, then just simply put -1 in that slot. So here's an example, right? So for example, we have example one here, and we have that's the list of numbers, and we have 5 numbers, and then we have 3 queries. So the answer will be a 3 integers. And so for the first one, right? So since the 0 and 1 are only 2 integers, not greater than 1, right? And then that's why no, we just pick the biggest one between the x or 3, 0 x or 3 and 1 x or 3. That's why we have two. That's why we have 3. So same thing for second query and the third query. And here's an example. So for example, this one here, since there's no numbers which is smaller than 1, right? That's why we have -1 here. And here's the constraints, right? So the length the length for the nums and the queries, they're all 10 to the power of 5. And the numbers of xi and mi, they are within like the integer, right? 10 to the power of 9. So that's that, right? I mean, the obviously the brute force way will be what? So we just for each of the queries, right? We loop through all the numbers, and for each of the numbers we do XOR, right? For any each of the number who is not greater than the current than this the m here, we do XOR with 3, and then we just get the maximum of that, right? I mean, obviously that's gonna be O of n square solutions, right? And with these constraints, that will TLE. That's what, and so which means we need to find a better way. That's what makes this problem a hard problem. So for this kind of maximum bitwise bitwise OR, right, within a bunch of numbers. So a common trick to reduce the time complexity is to use like a bit try. Basically, we use a try, we will build a prefix try here. Sorry, a prefix tree. Yeah, so the prefix tree also called a try. So the pronunciation is a little bit weird. So probably I'll just call it a prefix tree. So because that's more it's more common. So this prefix tree has like only has one node will only has up to 2 child nodes. Either we have zero, or we have 1. And we just build this prefix tree with the numbers here. so that in every time when we have like this numbers, we will basically try to get the bit values from the highest position, right? From the leftmost locations, and then we build it from left to right. So, and why this prefix tree can help us solve this problem, right? So the reason being is that since the numbers, right? Since the numbers are within the bit 10 to the power of 5, so which means that at most each number can have like up to 36 bits. Okay, and since we only have 32 bits, and um, commonly, whenever we want to calculate the bitwise OR, we always consider the values bit by bit. So let's say, for example, I'll give you the very simple example here. Let's say we have like 1, 0, 1, 1, right? So let's say we have this number here. Let's say this is the x. Yeah, let's say this is the x. So what's this number? That's the 8 plus 3, that's 11, right? So to be able to get the maximum number, we do a XOR, right? We do a XOR with some numbers here, with some numbers here. So in order to get the max values, so what's gonna be the biggest value we can ever get for this one? So ideally, what we can get is what is 1, 1, 1, 1. Right? So to be able to get us this 1111, so what's going to be the ideal candidates for this one? So we're hoping there's a number that have a bit value like 0, 1, 0, 0. Right? So if we have such numbers with this bit values, then if we do a bitwise with the current x here, we can get 1111, which is our ideal answer. Okay. And then how can we know if there's a number that has this 0100? That's when we need to use this prefix tree with like this 0 or 1 as a child node. So so here's how this prefix tree works. Let's say we have four numbers. Let's say we have a 1 0 1 1. We have and then we have 1 1 0 0 0 1 0 1, and maybe I don't know, maybe 0 1 1 1. So let's say we have these four numbers, and our x is what? X is, let's say we need uh the x is 0 mm, 0 1 0 1. How about this one? Yeah, I'm just giving you like a random example here. So let's say we have a 0 1 0 1, and that's the four numbers we have as candidates. And then how can we use this tree to find our final answer? So the way we're doing it is we're trying to match the bit greedily from the highest position, which is the leftmost location. So the reason we can do it in this way is because, as long as we have like a bit, we have a target, we have a value on the leftmost position, that's where we're gonna mark it as one, because the earlier we can mark the higher bit position as one, the bigger value we can get. So that's why we check the leftmost bit position. We see if we can have like a number that can satisfy this bit value to be one after doing the bitwise OR. So we have 0 here. So what numbers we're looking for? We're looking for 1, right? So for this one, the target bit will be the value will be 1. And then we'll see, okay, do we have numbers that has a starting has a 1 value at the current value at the current bit position? Yes, we have 2. Okay, so we will have this 2 here. That's why we have this bit value here, right? So we basically we have 1 1, and then here we have a 1 0 and 1, right? And then from 0 we have a 1, right? And then from 1 we have a 1. So from here we have a 1 1, and then we have 0, and then we also have a 0. So here it's 1, right? So that's why the way we're using this prefix tree is that we start from the root node, and then we see, okay, if the current one has like a child has a 1 value as 1, then okay, we find one because one there's a child here, and then we move to the second bit value here. So now what do we have? We're looking for 0, right? Because 0 bitwise XOR 1 will become 1. Do we have a 1 here? Because remember, we're at this node here. And then we're checking, do we have like a 0? Yes, we have 0. That's why we'll go here. We'll go to this route, right? Basically, we're going this way, right? And then the next one, we're looking for 1, right? So do we have a 1? Of course, yes, we have 1 because the next one is 1. But for the last one, we're looking for 0. Do we have a 0? No, we don't have a 0 because all we have is 1. So that's why, the best number we can find is it's going to be a 1 0 1 1. That's going to be our best answer. And how about what's going to be the answer? You know, basically every time when we find a match with the target bit values, we can accumulate. Basically, we can add the answer because here we find like the match, which means that we have at least we have 2 to the power of 3. Okay, and then for the second one, we also find a match, which means that we can add another 2 to the power of 2. Right, and then here we also find 1, right? So, and then we have a 2 to the power of 1. But in the end here, we didn't find a match. That's why we don't have anything to add here. So in total, the best answer we can get is like this 8 plus 4 plus 2, which is 14 in this case. Because in the end, what we can have is 1, 1, 1, and 0. And this is 14. So, and as you guys can see here with this prefix tree here, as long as we can follow a path, right, greedily, right, by looking for the match with the highest bit positions, we can just traverse down this prefix tree, and then we can just use the current path to see if we can find the match for the next bit value. If we can, and then we just accumulate the answers with the current bit position. Otherwise, we just skipped. Yeah, so basically that's how we're gonna use this this prefix tree to help us quickly calculate the a match between all the available numbers. Okay, and then the last thing is that since we also have like this constraint with m, right, which means that we're only considering the numbers that's not greater than m. So which means that we cannot just build the prefix tree with all the numbers. We have to follow some sequence. And then what's going to be the sequence we're following here? We can, what we can do is we can sort these numbers from the smallest to the biggest. Okay. And then we also sort these queries by the by m, from the smallest m to the biggest m. So after doing that, we can just every time when we have like a queries here, we can just grab all the numbers who is smaller than the current m, right? And then we can just build a prefix tree on top of that, because next time when we have like another m here, which is greater than the current, which is greater than the previous m here, all we need to do is just that we can just grab the a few numbers, right, after the last position, so that we we can only add these numbers in the prefix tree once by following this sequence here, right? So otherwise, if we don't sort this one, so for each of the queries here, we have to loop through all the numbers, right? We have to find all the numbers that's smaller than the current m, and then we build the prefix tree. That's going to be too slow. Uh, so that's why we need to sort. Okay, so enough talking. Let's start coding here. And so first thing first, right? Let me create a node for my prefix tree, right? So I'm going to have a node here, and so init dot and then self, and then here all I need is just a children here, right? So children is like another dictionary, right? And here we at most we'll have two children, but I'm still using like dictionary here. So here, and we have a root equals to node, right? And then to build the prefix tree, we need an insert, right? And then we have a query, right? So we have a two query, and here I'm creating all the signature of the methods first, and then we can implement those two methods later on. And then here, assuming we have those kind of insert and queries, and then all we have is the length of nums, right? We have this n here, and then like I said, I sort the numbers, right, from the smallest to the biggest. And then I also need to sort the queries, but after sorting, we will lose the original order, but which we still need to output, right? To do the output. That's why I'm going to create a new queries object, right? A list with the original index, and the xm for I dot xm in enumerate queries. Okay, and then I can sort key going to be the lambda of the x2, right? So this one, the m, we're sorting on top by that. And then I need the answer, right? So the answer is -1 at the beginning. I'm giving it all -1, so length of q. And then for I, x, m in the sorted queries, I also need a j, right? So to tell us what was the last position we added, we have added the numbers to the prefix tree, right? So while j is smaller than n and nums j is not greater than m, then we just do an insert. We insert this one into the prefix tree, and right, we do this, and then here we just do a nums populates answers I with a query of x. Okay. Yeah, actually so about the -1 case, right? So how about the -1? And we only do this when if the j is greater than 0. So here it means that if the j is one, sorry, if the j is zero, it means that there's no numbers that's gonna be smaller than the m. That's why then we can simply just leave this minus one, and we only do the XOR when there's something, right? When there is any something that is smaller than m, and then in the end, I just return the answer. So that's the main structure of this of this of this problem. And now let's try to implement this insert and the query. So for current, so to insert is like similar like the original like prefix tree implementations. So the only difference is that for each of the numbers we're gonna loop through from the highest bit to the lowest, which is the starting from 31 to 0. Okay, and so we have bit values. So we're gonna calculate the bit value of the current one. It's gonna be the what we just move shift to the right, and then we do a and one. That's how we get the value of the current bit. And if the bit not in the current dot children, right? And then we do a current dot children dot bit equals to the new node. Okay, and then we just move the current node to the next one. Okay. Yeah. So which means that if there's like a multiple like numbers that has the values at the same node, we just simply ignore it and we keep moving forward, right? And for the queries, right, like I said, so we also starting from the root, and then at the beginning we have zero equals the answer equals to zero, and we also from loop through from the for I in range of 31 -1 and -1. So the target, right? So remember the target. The target is actually the opposite value of the current bit, right? Because again, right, we're trying to get the max numbers, which means that since for x bitwise OR, if the current bit is zero, we're looking for one. If its current value is one, we're looking for zero. That's why so the current bit value is this one, and to be able to get an opposite values, basically we can just copy this one, and then we can do a XOR 1. That's how we get the target. So if the target exists, right, in the current children, so it means that okay, we have a match of our target values. Then we can just accumulate the current answer with the current bit value, right? With this one, if this current bit is 3, then it means that we can accumulate 8 to the answer, and then we just move the children, right? We also move the node to the next one, the target one. Else, else, if there's no match, obviously there's no new uh, values to be accumulated, and then the next value will be what? Will be the current equals to it's gonna be actually the original bit, right? So it's gonna be the target. We do another one. We basically we flip the bit value one more time, and then in the end we return the answer. Yeah, so for this part, I mean, okay, so I'll repeat this part one more time. So first, we're getting the target, right, which is the opposite value of the current bit, right? And if there is one, then we will go to the basically we'll of course we'll go there, and then we're accumulating the answers. If the target is not there, if the target is not there, and then it means what? So it means that since we're only having two nodes, it's either zero, and sorry, it's if we don't have a zero, then it means that the child has to be one, right? Because we're having at most two nodes, but at least one nodes, right? So there's no way that the current one doesn't have a child, because when we build the the prefix tree here, so you see that we starting from 31, and we build the tree all the way to the 0 bit, which means that at least a node will have like a node. So if the current one doesn't have the target node, then it has to be the opposite value of the node. Okay, that's why if the target is there, right, and then we of course will go with the target node path. If the target is not there, we know that, so the child has to be the opposite value. That's why we can safely go to the other values path. Cool. I think that's it. Or let me run the code. Okay, accepted. Okay, run. Yeah, so accepted. So for the time complexity, right? The uh, the insert and the queries for the prefix tree, because since we have at most 32 operations, so we can treat this insert and query to both O1 here. And then actually the only thing left is just these two sorts here. That's gonna be the sortings we have here, because the sorting is like n log n, right? Here we also have a n log n, and here is just a n. That's why the total time complexity for this one is gonna be the n log n. Yeah, yeah, I think that's it, right? So for this problem, I think it's one of the things we learned from this problem is that so next time when we are trying to get the maximum, remember it has to be the maximum. The maximum bitwise XOR values between one number and a group of other numbers. And we're trying to find the maximum. This prefix tree is a good way to improve our performance, since we have we have we have given like the x here, we know our target, right? So we just get our target value bit by bit here, and then with this target values, we'll traverse this prefix tree from top down, and then we'll try to find a match. We'll find a node with this target value. If it is, then we can accumulate the values for that bit position, and then we go with that. Otherwise, we just continue our traversing until we reach the last bit position. Cool. I think I'll just stop here. And thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.